Assistant Professor of Mathematics, A.D.M. College for Women, Autonomous, Nagapattinam. Today we are going to discuss about the topic sequences and series. This is a subject for second BSc Mathematics. It's a major subject, and in this subject we are going to see now about infinite series. We already studied about the sequences, and as a continuation of that part we are going to see the infinite series. Let us see the definition. So definition: let sequence AN be a sequence of real numbers. Real numbers. And the formal expression A1 plus A2 plus A3 plus etc. AN plus etc. is called the infinite series of real numbers. Infinite series of real numbers. So from a sequence we are getting the infinite series as the given expression A1 plus A2 plus A3 plus etc. AN plus etc. Let us consider S1 as the first element A1 and sum of first two elements as S2, which is equal to A1 plus A2, and S3 as A1 plus A2 plus A3, that is the sum of first three elements etc. And Sn as the first n elements, sum of the first n elements A1 plus A2 plus etc. An. Then the sequence Sn is called the partial sum of the series, and this series of real numbers is denoted by summation An or summation n equal to 1 to infinity An. So the infinite series is denoted by summation An or summation n equal to 1 to infinity An, and this Sn, sequence Sn, is called the partial sum of this series summation An. Now the series converge or diverge or oscillate according to this partial sums. So the series summation An converge, diverge or oscillate according as this partial sum Sn, the sequence Sn converges, diverges or oscillates. Converges, diverges or oscillates. So if you are given a series of numbers, then we have to check whether the partial sum of that series is converging or diverging or oscillating according as the series summation An converge, diverge or oscillates. So let us see one example. Consider the series one plus etc. Consider the series. So first we have to find the partial sum of this series. So first n elements, sum of first n elements, and it also 1 plus etc. n times 1 n times, that means which is equal to n, and clearly the sequence Sn, which is equal to n, diverges to infinity, and according to this sequence the given series 1 plus etc. is also diverges to infinity. Next let us see the behavior of the geometric series 1 plus r square plus etc. r power n plus etc. Example 2, consider the geometric series one plus r square plus etc. plus r power n plus etc. So now we are going to discuss the convergence behavior of this geometric series, whether it converges or diverges or oscillates according to the limit value or varies. Therefore, case one, before going to the case, let us find Sn, that is the partial sums of the given series. So up to nth value we have to get 1 plus r plus etc. r square plus etc. r power n minus 1, r power n minus 1, the sequence of partial sums Sn. And we know one formula for 1 plus x square plus etc. plus x power n minus 1, one formula, that is 1 minus x power n divided by 1 minus x. And using this formula we get Sn as 1 minus r power n divided by 1 minus r. So using this we are going to discuss about for the various cases. First let us consider case 1 as, let r varies from 0 less than or equal to less than 1. So when r value varies from 0 to 1, what are all the values we get? Maybe it is 1 by 2 or 1 by 3 etc. Then the series becomes 1 plus half square plus etc. Then now Sn is equal to 1 minus r power n divided by 1 minus r, and for this value, for the value r is equal to 1 by 2 or 1 by 3 or 1 by 4, anything else between 0 and 1, this sequence r power n converges to 0. This problem is discussed in sequences, and as this sequence converges to 0, this Sn becomes 1 divided by 1 minus r. Therefore, the sequence Sn converges to, 1 divided by 1 minus r. Therefore, summation, given summation, that is 1 plus, given geometric series 1 plus r square plus etc. r power n converges to 1 divided by 1 minus r if 0 less than or equal to or less than 1. So this is the first case. Next let us consider the second case. So case 2, let r greater than 1. Then let r value is greater than 1. Then clearly the sequence r power n. What are all the values of r? If r is greater than 1 means r may take the values 2 or 3 or 4 etc. Then we get the series 1 plus 2 square plus etc. 2 power n plus etc. And these values diverges as it is not bounded above, therefore it diverges to infinity, and clearly the sequence partial sums, the value or sequence r power n diverges to infinity. Therefore Sn also diverges to infinity, and finally it implies the given series, geometric series also diverges to infinity if r value is greater than 1. Next let us see r is equal to 1. So next case 3, let r value is equal to 1. So if r value is equal to 1, then the geometric series becomes, the series will be 1 plus 1 square plus 1 plus etc. 1 plus etc. And obviously this Sn is equal to n times 1, and clearly sequence Sn diverges to infinity, and therefore the series is diverges to infinity. Diverges to infinity. So we have considered we have completed 3 cases. First case, 0 less than or equal to or less than 1, and second one or greater than 1, and third one or is equal to 1. So here it converges, here it diverges, and here also it diverges. And the next case, case 4, let R value is equal to -1. Let R value is equal to -1. Then the series will be, what we get? First is 1, and next one is -1, as it is -1 the whole square, therefore 1 minus 1 and +1 -1 +1 -1 etc. like this. So if R is equal to -1, the series will be like this. Now we have to calculate the Sn value. For Sn, if n is even, then it gets cancelled. Even terms means for 2 terms 1 minus 1 gets cancelled, for 4 terms also it gets cancelled, and for all even values the series gets cancelled, and it is equal to 0 if n is even. And if suppose n is odd, then we get one positive value as extra value, other values get cancelled, therefore we get +1 if n is odd. Therefore the partial sums Sn oscillates. If n is even, it converges to 0, and if n is odd, it converges to 1. Therefore the partial sums Sn oscillates finitely, as the values are finite values. Sn oscillates finitely, and therefore the given series is also oscillates finitely. Oscillates finitely. Therefore case 4, when is R is equal to -1, it oscillates finitely. And the last case, case 5, let R is less than -1. When R value is less than -1, what will be the series? Maybe R take the value less than -1 means it may be -2 or -3, -4 etc. And the series will be, suppose if R is equal to -2, then the series will be 1 minus 2 plus 2 square plus 4, that means, and minus 2 cube plus 2 power 4 etc. So we have both positive values and negative values, alternate values. So the positive values increases 1, 2 square, 2 power 4, it increases, and it diverges to plus infinity, and the negative values, it diverges to minus infinity. Therefore Sn is equal to plus infinity and minus infinity for the positive values, and it diverges to minus infinity for the negative values. Therefore the given sequence Sn oscillates infinitely. Given sequence oscillates infinitely, and hence the given series also oscillates infinitely. Series also oscillates infinitely. So for the geometric series, we have considered 5 cases, less than -1, and here it oscillates infinitely. So out of these 5 cases, for the value R varies from 0 to 1, it converges, and for the value R greater than or equal to 1, the given series is diverges, and for R less than or equal to -1, the given series is oscillates. So next, let us consider the series As a third problem, consider the series 1 plus 1 by 1 factorial plus 1 by 2 factorial plus etc. plus 1 by n factorial plus etc. So we have to discuss the convergence of this series. Now let us take the sequence of partial sums Sn 1 plus 1 by 1 factorial plus 1 by 2 factorial plus etc. plus 1 by n minus 1 factorial. And already in the sequence part, we have proved that this sequence Sn converges to the value E as it varies from 2 less than the anth term or snth term less than 3. So it takes the value E, therefore the sequence Sn converges to E, and therefore the given series also converges to the value E. So already in the first problem we have discussed about the divergence of a series as an example, and in the second problem, geometric series, we have classified into 5 cases for the values taken by R from 0 to 1 and greater than 1, equal to 1 and less than 1, or equal to minus 1. And in this problem, we have given an example which converges to the value E. Next, consider the series 1 plus 1 by 2 plus 1 by 3 plus etc. plus 1 by n plus etc. And here, if we take the Sn as the partial sums, 1 plus, we get 1 plus 1 by 2 plus 1 by 3 plus etc. plus 1 by n. And as we have discussed this problem also in the sequence part, clearly we know that the partial sums Sn, which is equal to, which diverges to infinity, and therefore the given series also diverges to infinity. So in this part, we have seen what is the definition of an infinite series, and when will it converge, diverge or oscillates according to the sequence of partial sums Sn, and we have discussed 4 problems regarding the series about the behavior of the convergence or divergence or oscillation. And one more thing, it's a note, if we add some m number of terms into the series, that won't alter the convergence or divergence of the series. Thank you.